Oh yeah, what a wonderful day here. Frame relay, everybody's favorite. One good thing, it looks like it's a short one, right? Describe the benefits of frame relay. Explain frame relay operation. Explain bandwidth control mechanisms in frame relay. Configure a basic frame relay PVC on a router serial interface. Configure a point-to-point on sub interfaces. Show and debug. The good thing about this is there's not a whole lot of it on the CCNA. Frame relay rarely used nowadays. Probably never experienced. Not a whole lot of people using serial. Some do, I guess. But anyways, the stuff you're doing is pretty basic. So, and if you want an advanced frame relay, well then let me know. So, introducing frame relay. So we had lease lines before, right? And basically the problem with lease lines is they are expensive. Okay, and so that's what frame relay provides us with. Frame relay allows us to take one serial line, and even though we're going to be configuring point-to-point in this, it's typically a point-to-multipoint. And it's what we call a non-broadcast multiple access, and so it means slow bandwidth. Usually we take a T1 and we can separate it into, I think, like, is it 200K? I don't know. We can separate it into Ks, so we could probably drop it down to 56K if we wanted to. Probably wouldn't. It's faster than 56K typically, but we can form a circuit to here so that Dallas seems like it's connected to New York, and Mexico is connected to New York and Dallas, and Chicago is connected to who it needs to be. And that's what they're showing you in this frame relay service provider network, is really these places think they're just directly connected to them, even though they're just going over a serial. But they can actually go over one serial and go to multiple places. And that's what makes frame relay fun. What else is interesting? Historically, frame relay was used extensively as a WAN protocol because it was inexpensive compared to dedicated lease lines. In addition, configuring user equipment in frame relay network is very simple, and that's all we're going to be doing. Frame relay connections are created by configuring customer premise equipment, routers, or other devices to communicate the service provider frame relay switch. The service provider configures the frame relay switch, which helps keep end user configure tasks to a minimum. In most cases, we could probably set up an SVC where we just say, hey, encapsulation frame relay, and it gets all the information it needs. We'll also show where we don't do an SVC, and that's when it becomes more complicated. And here's the benefits of frame relay. As it says up here, with the advance of faster technologies, it makes frame relay kind of worthless. The bandwidth values used in the lease line frame relay examples throughput do not necessarily reflect the current bandwidth used by many customers today. Not many customers are using a 4K link, woo, or a 12K, woo. All right, so they're just showing you that we can break it into. What does it say? Does it tell us how much we can actually break it into? No. I think maybe it's 4K. So this must be what our smallest one we could break it into. But anyways, so what this is doing is we took T1, we break it down. We only pay for what we're using rather than paying for a T1 to here and a T1 to here, T1 to here. We can have one T1 go here instead of a T1 to Mexico and a T1 to Chicago and that kind of thing. We can break it down and have them go to different places, one T1, with these slow speeds. And that's what's showing here. Their dedicated line requirements. Be expensive, basically, I think is what they're saying. And so it says, dedicated line provides little practical opportunity for a one-to-many connection without getting more lines from the network provider. Whereas we can break them up the frame relay. That's what it's showing. Once again, you can read over that it's cost effective because we get this one dedicated line, and it does. Sorry about that. I forgot where we are, but anyways, with so it's cost less than our private lines. And then here's where we start getting some important terms. In frame relay, the end of each connection has a number to identify it called the data link connection ID identifier, a DELC. So from now on, when you hear DELC, it's a number that it's going to be like our layer 2 encapsulation. It says, hey, this layer 2 is switched to this layer 2, and so this DELC is mapped over to this DELC. And so remember, WAN is layer 2, and so how we're virtualizing that we are connected, even though we're going long ranges, are these DELCs. And so DELCs are, if we have a PVC, I think we have PVC on here. No, it just says PVC right there. So the PVC is this DELC maps to this DELC, and that is one of the multi-points. And then the other DELC, so there's two DELCs because this is one connection that's going to go 2 places, or it could go to all these places. So we'd have different DELCs providing different PVCs to different locations, and that's what we're going to be talking about here as we keep going. Alright, so let's make sure we've covered some of the and there's not really much those terms that matter for frame relay. So here's our virtual circuits, and these virtual circuits are a layer 2 thing. So this is where we're mapping DELCs. So let's see what it says. Bum, ba, bum, bum, bum. And it's hard to understand this with what we're doing here, but DELCs are important more when we have multiple connections, like where this is only one place going to one place. It's not as important. Let's see if this one gives us no, that doesn't give us multiple locations. But also DELCs are local to each switch, right? So this switch is determining the DELC, and as they're showing here, the DELCs can have different numbers, and they are important to the switch. Just as MAC addresses, remember, they're only important to each device, or each network, each DELC. We can, as this DELC can have a certain amount of DELCs that map to this one, but they don't. This one can start using similar DELCs, like it could use a 102 if it really wanted to. Anyways, but before we do that, switch virtual circuit. This is our probably most common because it's easy setup. This is where we just say, hey, on this interface, the internet service provider, which I can give you a similar thing, so where you can form your own frame relay cloud. So this SVC again, so it establishes dynamically. So when we see SVC, we say dynamic, as in just picks up the DELC if we set our encapsulation frame relay. Then we have PVCs, pre-configured by the carrier, and after they're set up, they only operate in data transfer and idle modes. Some publications refer to PVCs as private VCs. So this is where we'd actually put a map from, like we'd actually put in here, we'd say, hey, this DELC goes to this DELC, which goes to this IP address. Because remember, so since we're dealing layer 2, we'll find out that SVCs use a technology we have to map called inverse ARP, right? ARP was where we took a PC wanted to find a layer 2 address. Now we want layer 2 addresses to find IP addresses, so they use inverse ARP. Or with our PVCs, we set a map where they go from, we say this layer 2 address goes to this layer 3 address, something like that. And hopefully it'll make more sense as we go through this. Right here, locally significant DELCs, talk about that. I think that's about all we've covered right now. So we're going to keep going on. Multiple VCs. So this is what I'm talking about, where we have, right here we have 2 DELCs. One goes up to here, point to multi-point interfaces, and the other one goes to here. So we set up different VCs, one serial interface, different connections. And this is where what it's saying is this is where frame relay starts being cheaper. Frame relay encapsulation. So this is what's fun about frame relay is we have layer 2, and it's a layer 2 protocol. In it, it's giving us our DLCs. Then we are going to have this feckin, beckin, discard eligible, and I don't remember what the EA is. Do we have an EA here? Anyways, these bits are congestion control. Okay, so feckin is forward exclude congestion notification, and beckon is backward exclude notification. So if we can burst with these technologies, so we could actually pay for more when our lines aren't busy, we can get more speed, but these bits will say, hey, going through this switch, it starts setting the feckin, and it says, oh, coming back, it's busy, so going there, it's busy, going back, it's busy. If these start getting marked, then they become discard eligible, and so if it says, hey, it's busy, no more burst traffic, start dropping stuff. I believe that's basically our CR, DLC stuff, standard address, more DLC stuff. Not that important. You just need to know that the feckin and the beckon are allow for discard eligible. Once you hit discard eligible, if you get any congestion, it's going to start dropping it. So full mesh, partial mesh, frame relay, usually this hub spoke thing going on where we don't have a full mesh. Maybe we do. We could have full mesh. We could have something like well, that's with actual physical interfaces. With the frame relay, we have a full mesh through point to multi-point interfaces. As it says, each one has 4 virtual circuits going to the other hosts. Alright, so now we get to our inverse ARP. A primary tool of frame relay is inverse ARP. And so when we do the PVC, we actually turn inverse ARP off. Otherwise, it's running. And so ARP translates layer 3, right, to layer 2. Inverse ARP translates layer 2 addresses to layer 3. So our DLC gets translated to an IP address, as it's showing here. How do we do that? Well, so they've turned on inverse ARP, and so we're doing a manual frame relay map. So we say frame relay map the IP address of 10.111.2, and we're going to send it out 102. This broadcast, what this means is if we don't set it, it's not going to allow broadcasts out. So stuff like, well, even our multicast won't be going across there. So we need that broadcast to actually allow OSPF and EIGRP, if we want to use those routing protocols across our frame relay cloud, we need this broadcast in there to allow those to work. Otherwise, we don't have to put this if we are using inverse ARP. And I guess this actually is PVC, so I guess it just depends on how we're doing. I was thinking inverse ARP only worked on SVCs. Guess it's proved me wrong because it says inverse ARPs. Just request the PVC. And if you guys ever get confused with what a PVC is, I think of it as we a lot of times call our DLC to DLC links a pipe, right? So PVC pipe, plastic pipes. DLCs make PVC pipes. That's my little remembering. Or we can do static frame relay mapping right there, right? Otherwise, if we just did encapsulation frame relay and we have inverse ARP running, we just say encapsulation frame relay. And this isn't that common because usually we do sub interfaces with frame relay because we're doing point to multi-point. This is a point to point setup. Not very common. But anyways, we just do show frame relay map, and if inverse ARP was going on, it would bring this up. Alright, so now we have these weird little things with frame relay, right? Such as the LMI. The frame relay design provides a packet switch data transfer with minimum blah blah blah. Anyway, so LMI is a keep alive mechanic that provides status information about frame relay connections between the DTE and the frame relay switch, the DCE. Every 10 seconds or so, the end device pulls the network, either requesting a dumb sequence response or channel status information. If the network does not respond with the requested information, the user may consider the connection to be down. When the network responds with a full status response that includes status information about DLCs that are allocated to that line, the end device can use information to determine whether the logical connections are able to pass data. So we can do our show commands or show frame relay LMI. Shows the type of LMI being used, which we'll talk about in a second. Status exchange, including errors such as LMI timeouts. LMI is easy to confuse with encapsulation. The LMI definition of the messages is used between the DTE and the DCE. Encapsulation defines the headers used by DTE to communicate information to the DTE at the other end of the VC. So LMI is between here and here with the frame relay cloud. Encapsulation is from here to here, how we're getting it there. That's what that's saying. And where it gets confusing is we have different LMI types. So our LMI types are Cisco, default on Cisco. We can change it to ANSI or Q933A, and you can read about those. And we can do show interface, blah blah blah, and it's going to show us what our LMI is doing. To change our LMI inside of our interface, we say frame relay LMI type, say Cisco, probably not because it's set by default, ANSI, Q933A. So where this would actually probably be important is in our frame relay cloud. If we use Cisco devices, our internet service provider does not, we're probably going to have to change that LMI from Cisco. So what else do we have here? This stuff. Our extensions, VC status message, provides information about the PVC integrity, blah blah blah, multicasting, allows a single frame to be sent into multiple, right? Definition of a multicast. One-to-many provides connection. Global addressing provides connection IDs with global rather than local significance. So that's where our DLCs would be more important. Simple flow control, FEC and beckon. Using LMI and inverse ARP to map addresses. So this is what I've been talking about. And so if our LMI is set up, right, it's going to use inverse ARP to just set our configuration. And it says this DLC is active, so then we can send to DLC 100. What it's doing is it's going to give us the frame relay map rather than us having to set it with inverse ARP and the LMI setup. So anyways, probably want to try this. The only questions you'll get on your CCNA probably is like it's about virtual circuits, and if there's a frame relay map, what DLC does a computer use to send to another DLC, which is pretty apparent right here. DLC it's going to use is 432 to get to this IP address, and this IP address is going to use 152 to get to this router. Try out those definitions and you'll be good. Okay, so now here is more of our WAN level stuff. So access rate, the capacity of the local loop. So how much we have. The committed rate, CIR. This is where we start getting into WAN technologies, and we are guaranteed a speed. Rather than access rate would be like Cable 1 says you can get up to 200 meg. Okay, what are we actually getting? This is our guarantee of what our lowest, this is a guaranteed rate. So Cable One guarantees, if we had a CIR, we could guarantee 50 meg. That means we can complain and get discounts if we are not at 50 meg. Say if our CIR is 50 meg for Cable One, we could go up to 300, which is never going to happen, or 200, which is never going to happen, but we can never go under 50 meg. And so that's what these terms are. And so customers usually pick a CIR. Yeah, I don't know. You guys can read that. It makes sense. So then our next enterprise technology, bursting. So bursting is where we can actually pay for a burst. Committed burst size, BC, and excess burst size. So when the traffic's not busy, we get more speed than our CIR, right? So we're getting this burst rate, and this is usually pretty cost effective. And if we have a backup link, sometimes we can use frame relay as just a backup for some things, or any WAN technology. And instead of paying for a CIR or an access rate, we just pay for burst. And so we can use this backup link to do something without paying for very cheap. And so we can only use it when the line isn't that busy. Otherwise, it gets discard eligible when we're doing this bursting, and it will throw this stuff away when the line gets busy. So that's one thing. Flow control, fecken and beckon. Here's an example. We're sending to one place, bam, 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 forwarding. Okay, so each switch, depending on where it's sending something, when it forwards it, it could be coming busy, or when it's coming back, it could become busy. So forwarding, sending it there, or on the way back, because we go through multiple switches, and so these queues happen, and so these bits are set. I think that makes pretty good sense. Hopefully it makes sense to you. If not, read into some of that stuff. Basic frame relay configuration. We set an IP address, we set the bandwidth. Now this would be, remember, this is not a speed. This is used for EIGRP and OSPF to calculate the speed rates on these serial links. Then we set the LMI if it's not Cisco. Remember, on Cisco devices, it's Cisco by default. Then we just do an encapsulation frame relay. If we said no encapsulation frame relay, what's it going to do? It is going to send it back to HDLC. Alright, because remember, serial interfaces by default are on HDLC. But we can't form a frame relay link until we set it to frame relay. If we want to do the frame relay map, we saw this before, so we say frame relay map protocol. So this is either IP or IP version 6. Oh, what did I do there? And so if it's IP versions, we say that, and then we say our IP version 6 address or IP version 4 address. We say DELC, the DELC number, right? And then broadcast if we want it sent across. This broadcast word allows broadcast and multicast to be propagated on all nodes. When we use this broadcast, that's when we get that MBMA. Non-broadcast multiple access would be MBMA, would be where we don't allow the broadcast across. It's just these slower links with frame relay. We've seen frame relay in terms from back when we studied those protocols, but here's how we actually do that. Frame relay map, IP version 6. We did IP version 6 on this one. Set it there. Once again, this isn't very realistic in my opinion because this is just point to point, but that's all you're learning about here. If we did this in another way, we'd say interface S01 blah blah blah, S001. We wouldn't put an IP address on it, and we'd do a sub interface much like we did router on a stick, except we'd say interface serial 00/1 dot 1, and then point to multipoint. And maybe they will show us that here in a second. But what this is static frame relay, right? That we're seeing a static frame relay map. We don't have to do that if we're just using inverse ARP. but we probably need this show command. Show frame relay map is going to show us the map. If we're having problems, this is my first command I always go to. Then I check the LMIs if we're having problems there, and so on and so forth. Maybe you want to try it out. Go ahead. I definitely try this pack tracer out so you have a nice little frame relay that's working. So some unique problems. Anything when we have sub-interfaces, we have to do split horizon or disable split horizon. So split horizon, what it does is it doesn't allow EIGR updates from sub-interfaces, right? Because any update that's sent out here, it doesn't allow it coming back, but in this sense we need it because it's hub and spoke, and so we need the routing updates, and so we have to disable split horizon. We need, well, blah blah blah. Neighbor discovery DRBR link states such as OSPF does not use the split horizon rule, right? That's only for RIP and EIGRP. However, reachability issues can arise with the DR and BDR. OSPF over MBMA networks work in non-broadcast network mode. By default, neighbors are not automatically discovered. Neighbors can be statically configured. However, ensure that the hub router becomes a DR as shown in figure 4. So that's what figure 4 says. Call behaves like Ethernet, and on an Ethernet, a DR is needed to exchange routing information between all routers in the segment. Basically, it's just saying we still need multicast, but we probably are going to set our DR so that LSUs are set appropriately, right? Because remember, some LSUs go to DRs and BDRs, while other LSUs go to the druthers or anyone that is not a DR or BDR. Here's our sub interface. So one type of sub interface is point to point. So that's where we're just going from this device only goes to here, right? Point to point. That DLC only goes from this sub interface goes from here to here. This sub interface goes from here to here. This interface goes to here to here. So if we have one DLC that goes to multiple other DLCs, that's a multi-point interface. So that would be where we only have one DLC over here, and all three of these go back in, and they'd all be in the same network. As we can see right here, they're not in the same network. Maybe this one is actually doesn't show us an IP address. But anyways, multi-points go to DLCs in the same network. Configuring point to point. Here we go. Interface serial, sub-interface number, and then at the end of it, whenever we do this, it's going to ask if it's multi-point or point to point. We have an example. And this is where when we do sub-interfaces, we do have to assign a DLC number, right? Because it can't automatically assign it from inverse ARP because there are multiple interfaces that could be getting it. Here's your example. Here's your programming. Take a look at it. It's not much different. Anyhow, I'm not going to go over that much. If you are interested, this is one of the requirements of the CCNA, but as I said, they're taking more and more frame relay off of it, so I wouldn't worry about it too much. Verify, these are the show commands we're talking about. Show interface is serial, probably a good one. Show frame relay LMI, and show frame relay map. Show frame relay PVC. You're going to see your vecin and beckon bits. Yeah. Frame relay inverse ARP on by default. You can reset it if you need to. Troubleshooting. Debug frame relay LMI. We can figure out if we're forming our frame relay to our switch or if it's something else. Probably would call an ISP at this point for the most part. Unless you are the ISP, that's where this would be important. Unless you won't have to worry about it. This looks like a good one. This includes frame relay, PPP with CHAP, and EIGRP static, and default static routing. I'd definitely take a gander, try that out, because at this point you're expected to know how to do all of that stuff. So that was a pretty short one, 30 minutes. Hopefully I didn't go through it too fast, but I didn't want to bore you with the beauty of frame relay. Anyhow, hope you enjoyed it. If you have any questions, please send